expansion refers to a change in the volume of a substance due to a change in its temperature. The word expansion in the previous expression might be misleading. This is due to the fact that although the temperature increase results in a volume increase or expansion in most materials, some materials experience a net volume decrease or contraction with increasing temperature. Another material property that's closely related to thermal expansion is isotropy. An isotropic material is one whose properties are uniform or the same in all directions. Hence, when the square that is made of an isotropic material that expands with temperature is heated, it still remains a square, since all its dimensions change by the same proportion. An anisotropic material, on the other hand, is a material whose properties are non-uniform, or are a function of direction. Hence, when the square that is made of an anisotropic material is heated, its shape becomes distorted, since one dimension changes by a different proportion than the other. Thermal expansion has many applications in our daily life. Bridges usually have expansion joints between their different sections that allow these sections to expand freely when the temperature is high, without distorting the bridge structure. Railroad tracks also always have small gaps between them. The gaps allow the rails to expand slightly when the temperature is high. If the gap was not present, the thermal expansion could cause the tracks to become distorted, which could lead to a derailment. If you look at a power line in the summer, you will see that it is sagging somewhat. In the cold of the winter, however, much of this sagging is gone, due to the contraction of the power line at low temperature. If the extra length of power line that causes the line to sag in the summer was not present, the line could snap, or cause its supporting tower to collapse as it pulls on the tower, due to its contraction at low temperature. When concrete slabs or brick walls are laid, a small gap is usually left between different sections of the slab or wall. This allows the concrete slab or brick wall to freely expand. If the gap between concrete slabs is not present, or not big enough to accommodate the largest expected expansion of the material, the slab can crack due to thermal expansion. The molecules of a solid or a liquid oscillate with an amplitude that depends on their internal energies. Since the internal energy is a function of the temperature, the amplitude of the molecular vibrations is also a function of the temperature. In a way, the molecules behave like point masses that are connected by springs to other nearby molecules. As the temperature increases, the amplitude of the oscillations of the molecules also increases. This causes the molecules to move further apart, which results in the volumetric expansion of the material. When an object that is made from an isotropic material undergoes thermal expansion, all the dimensions of the object increase by the same proportion. In other words, thermal expansion of an isotropic material is kind of like looking at an object through a magnifying lens, where one sees all the object's dimensions bigger by the same proportion. Hence, the hole in the shown pulley does not become smaller as the surrounding material expands into it. Rather, the hole expands proportionately as the pulley is heated. Over a small temperature range, the change in the volume of a solid or a liquid is proportional to the original volume and to the change in temperature. Hence, we can write that the change in volume, delta V, is equal to the initial volume V times the change in temperature delta T, times a proportionality constant alpha sub V. Alpha sub V is called the coefficient of volume expansion, and it has SI units of Kelvin to the -1, or degrees Celsius to the -1. In other words, the final volume, minus the initial volume, is equal to the coefficient of volume expansion, times the initial volume, times the final temperature minus the initial temperature. In differential form, we can write that the change in volume, divided by the change in temperature, is equal to alpha subscript V times the volume. In general, the coefficient of volume expansion is a function of the temperature. The coefficient of volume expansion is also usually positive, which means that for most substances, when the temperature increases, the volume also increases, and vice versa. Shown here are two tables that contain the coefficients of volume expansion for some common solid substances and some common liquid substances at a temperature of 20 degrees Celsius, unless otherwise noted. The values of the volume expansion coefficients in these two tables were multiplied by 10 to the power 6, to avoid having numbers with decimal points and too many leading zeros. The units for alpha V in these two tables are in Kelvin to the power -1. Notice that for liquids, the coefficient of thermal expansion is usually higher than for solids, due to the fact that liquid molecules are freer to move with respect to each other. Also note that concrete has a wide range of thermal expansion coefficients, since its coefficient depends on the type and composition of the concrete. Also note that Pyrex, which is a special type of glass used for cooking utensils and lab equipment, has about 1/3 the thermal expansion coefficient of regular glass. Invar is a nickel-iron alloy that is used in applications where thermal expansion must be kept to a minimum. The coefficient of volume expansion of water varies greatly with temperature, and is actually negative at temperatures that are close to 0 degrees Celsius. The cause for this peculiar behavior of water will be discussed in the later section. One application of the volume expansion of solids is shrink and expansion fitting. Shrink and expansion fitting are techniques that are used to join components that don't fit together when they are at room temperature, like for example, the shown shaft and pulley. Note that the diameter of the small section of the shaft is slightly larger than the diameter of the pulley's hole. Hence the shaft and pulley do not fit together. In shrink fitting, the pulley is heated, which causes it to expand. Since the pulley's hole is now bigger, the pulley can be mated with the shaft. Subsequently, the pulley cools down to room temperature. As the pulley contracts, the size of its hole decreases, creating a tight fit with the shaft. The expansion fitting is very similar to shrink fitting, except that in this case it would involve the shaft being cooled, in order to contract before being fitted into the pulley. One application of the volume expansion of liquids is the glass thermometer. It consists of a bulb that is filled with a fluid. The bulb is connected to a long tube, within which the fluid within the bulb can expand when it is heated. A scale that is attached to the tube converts the distance that the fluid travels up the tube into a temperature reading. For the shown thermometer, the temperature reading is 80 degrees Fahrenheit, as indicated by the length of the liquid in the glass column. The bulb of a mercury glass thermometer is completely filled with 1 milliliter of mercury. It is connected to a narrow circular tube into which the mercury can expand. The diameter of the tube is equal to 0.1 millimeters. Without taking the glass expansion into consideration, what is the distance through which the mercury has to rise in the thermometer's tube to indicate an increase of 1 degree Celsius in the ambient temperature? The volume expansion coefficient of mercury is equal to 182 times 10 to the -6 Kelvin to the -1. We are given that the volume of mercury within the thermometer bulb is equal to 1 milliliter, which is 10 to the -6 meters cubed. The diameter of the thermometer's tube is 0.1 millimeters, or 10 to the -4 meters, and the change in temperature for which we should find a change in height of the mercury in the tube is equal to 1 degrees Celsius. We can use the formula for volume expansion to find the change in volume. Delta V is equal to the volume expansion of mercury, times the volume of mercury in the thermometer's bulb, times the change in temperature. By plugging in the values of these variables, we get a change in volume of 1.82 times 10 to the -10 meters cubed. The extra mercury volume will rise into the thermometer's tube, which is cylindrical in shape. Hence the change in volume of mercury within the tube is equal to the volume of a cylinder that has a diameter d, and a height delta h. Thus delta V is equal to pi times d squared over 4 times delta h. We can rewrite this equation as shown, and solve for delta h by plugging in the values of the variables. and we find that delta H is equal to 0.0232 meters. Thus for every 1 degree Celsius rise in the ambient temperature, we get a change of height of 2.32 centimeters for the mercury in the thermometer's tube. Next we will study the phase diagram of a typical substance, how the specific volume of liquids and solids varies with temperature at constant pressure. Typically for liquids, as the temperature increases, the specific volume increases, indicating volume expansion with temperature. Similarly for solids, as the temperature increases, the specific volume also increases. Notice also that typically, for the same change in temperature at constant pressure, the change in volume in the solid region is generally smaller than the change in volume in the liquid region. This is in accordance with the generally observed fact that for most substances, the coefficient of thermal expansion of the liquid phase tends to be larger than the coefficient of thermal expansion of the solid phase.